Hello everyone, today we're looking at the topic of friction in mechanics and working with rough surfaces. Now previously we've dealt with questions on smooth surfaces, meaning there is no friction whatsoever. So we're now applying this to rough surfaces where friction comes into play. Now if you think about when you try and move something on a rough surface, it depends on a variety of different things. First of all, if I try pushing something which is heavier on a rough surface, it is going to be more difficult to move. So if I imagine I've got a heavier object here, the frictional force will increase. But also, if you imagine trying to push something and you add more force to it in a downward direction, that also makes it more challenging to move. So friction actually doesn't just depend on the weight or the forces acting down. What it comes down to is the reaction force or the normal reaction force that is acting on the object itself. So as this value of R increases, the frictional force will increase as well. The other thing it depends on is how rough the surface is. And this is called mu, or the coefficient of friction. The rougher a surface, the larger the value of friction. So friction actually depends on two things, mu and R. Mu as a value varies between 0 and 1, where 0 is a surface that's completely smooth and 1 is a value that is the maximum that the coefficient of friction could be. So let's think about this logically. Let's say, for example, the value of mu r for this scenario over here is equal to 50 newtons, and I start pushing forward with a value of 20 newtons. Now, what would be the value of friction in this case, and which direction would friction act in? Well, friction very clearly will always act in the direction opposite to motion, not opposite to the forces, opposite to the motion that is taking place. So if we think about this, friction is going to take on a value which we need to work out. Now, most people, or a lot of people, will say, oh, friction is equal to 50 newtons because mu r is equal to 50 newtons. Now, if friction was equal to 50 newtons, there would be an imbalance of the forces over here. The 20 newtons is less than 50 newtons, meaning that this would push in this direction due to a net force of 30 newtons to the left. But that doesn't make sense. If I'm pushing this way with 20 newtons, I'm not going to end up moving this way. So friction in this case would actually match the value of the 20 newtons to maintain equilibrium. If I now increase this force up to 30 newtons, if I increase this force up to 30 newtons, I still haven't overcome friction, so friction would also increase up to 30 newtons to keep this system in equilibrium. Now, this would keep happening until I reached a value that exceeded 50 newtons. When I get to 50 newtons over here, friction still has not been overcome, but it finally comes to its maximum value, which is now 50 newtons. The moment I overcome 50 newtons, so if I now push this up to 51, or to keep this simple, up to 60, I've now exceeded the maximum value of friction. Friction can't go larger than 50. So we would now have a net acceleration to the right-hand side because there is now an imbalance of force. What this means, therefore, is that friction is less than or equal to mu r. And we did have a scenario a moment ago where the 50 newtons was equal to the 50 newtons. And this is what we call the limit of equilibrium, or limiting equilibrium. When friction is equal to the value of mu r, we call this Fmax, and that's equal to mu r. We call that limiting equilibrium because it has reached the limit of equilibrium. If I exceed this value anymore, it will no longer be in equilibrium, and that's a very, very key thing to understand, which we'll look at for some of our later questions. So I'm first going to just show you 3 scenarios which we are going to work out the value of friction for. So over here, I have my three scenarios. I've got a force, a block of, well, 3 blocks of 5 kilograms. I've got a force of 2 newtons in the left, 4.9 newtons in the middle, 10 newtons on the right, and a value of mu equal to 0.1 in each of these scenarios. And the first thing we're going to do is to label our forces. The forces acting on each of these, there is weight of 5g, 5g, and 5g. There is also a reaction force acting upwards of r, and r. And because there are no other forces acting in the vertical plane, r must be equal to 5g in each case. So r is equal to 5g in each case. There is also friction, we said. Friction is acting in the direction opposing the motion. So there's friction over here, and friction over here. And we have said that friction is a value that is going to be less than or equal to mu r. So first of all, we said r is equal to 5g, which is 49. We've said mu r is equal to 5g times by 0.1, which is 0.1 times 49 is 4.9 newtons. So let's look at each scenario individually. On the left hand side, the 2 newtons is less than the 4.9, less than 4.9 newtons. So if the 2 newtons is less than 4.9, we are not exceeding friction. Therefore, the friction must be equal to 2 newtons to keep this in equilibrium. That is our scenario on the left. Scenario on the right, or sorry, in the middle, friction is now equal to 4.9. 4.9 is equal to 4.9. Therefore, we are now at Fmax, which is equal to 4.9 newtons. And that means we are in limiting equilibrium. If I exceed this value of 4.9, I'm going to be accelerating. And that is exactly what happens in the scenario on the right. Friction here is going to be equal to 4.9 because 10 newtons is greater than friction. So this is equal to 4.9. Now I'm just going to work out the acceleration in the scenario on the right hand side using F equals to ma. F equals ma to the right. My net force is 10 minus the frictional force of 4.9 is equal to 5 times by a. That gives me 5.1 is equal to 5a, and therefore from that a is equal to 1.02 meters per second squared. Very, very clear situation here that we've said that over here friction was less than mu r, here it was in limiting equilibrium because it was equal to mu r, and here we had an acceleration. So we're going to look at one final example over here, and we are going to apply this to a question which has a few other forces being brought in. Now we can see the key difference in this question is we've got this force X acting at an angle. Now what this is going to do, or what this is going to enable us to show, is the value of R will be a little bit different to just the weight. Because if we label our forces, we have our 10 kg coming downwards, or 10g acting downwards, our weight. We have our reaction force acting perpendicular and up. Now previously we said R was equal to 10g, but that won't be the case here, because if we think about X can be resolved into the vertical and horizontal direction, or the parallel and perpendicular direction, where we have X sine 20 acting downwards and X cos 20 acting to the right. Let's make that a little bit clearer. X sine 20. And we also have friction acting to the left. Over here we have our frictional force. So now R is not just equal to the 10g, but it's also equal to 10g with the 10 sine 20, because those are both acting down. So we are providing more force in the downward direction, making it more difficult to move. So the first thing we can say is that if we think about the forces up equal to down, R is equal to 10g plus X sine 20. Now, our value of mu in this case is 0.9. That means it's a very rough surface, a lot rougher than what we dealt with previously. So if we work out the value of R when it's 100 newtons, 10 times 9.8 plus 100 sine 20 is equal to 132.2. That's equal to 132.2 newtons. That means that mu R is equal to 132.2 times by 0.9, which gives us 118.98. 118.98 newtons. That means friction is going to be a value either equal to or less than 118.9. And what we're looking at is whether x cos 20 is going to overcome that. So let's take a look. Does x cos 20 overcome that? So 100 cos 20, let's use a different pen. 100 cos 20 is equal to, on your calculators, is equal to 93.96 or 93.97 newtons. Now, that is not greater than mu R. Therefore, the value of friction in this case is also equal to 93.97. Friction is equal to 93.97 because we have not overcome the value of mu R, meaning this particle, this object is not going to move. So that was when we used it for x is equal to 100 newtons. Let's now apply this for x is equal to 1,000 newtons. So up is equal to down means the value of mu R is now going to change and the value of R is going to change. So let's get rid of all of that, get rid of all of that, and get rid of all of that. We can see over here that if we apply the same process, R is equal to 10g plus now 1,000 sine 20, so 1,000 sine 20 plus 10 times by 9.8 is equal to 440 newtons. So this is now equal to 440 newtons. If we multiply that by 0.9 to get our value of mu R, so times by 0.9, gives us 396 newtons. 396 newtons. And now we need to see if x cos 20 is going to overcome that. So if we work out the value of x cos 20 or 1,000 cos 20, 1,000 cos 20 is equal to 939.69 or 939.7 newtons. That means friction is equal to 396, and it means that this particle is going to accelerate to the right hand side. So we can actually work out that acceleration using F equals ma. If we apply F equals ma to the right, x cos 20 is my positive force minus mu R is my negative force is equal to 10 times by A. X cos 20 is 939.7 minus 396 is equal to 10 A, and therefore if I work that out, we end up with a value for our acceleration equal to 54.4 meters per second squared, a very high acceleration, meaning that force is a very, very large force in overcoming our frictional force. So 54.4 meters per second squared. So what we've done here, as we said, it was follow the same process. For each part of this question, we first worked out the value of R. We first resolved our force and then worked out the value of R. We then applied this to mu R and determined whether or not our horizontal force overcomes the value of friction. And then we worked out the acceleration if required. I hope that's made sense. If it hasn't, please comment below or let me know privately. Thank you very much for watching. Take care.